Hi there, and welcome to WOMAD 2020 World of Physics. My name is Lukas, and I'm a particle physics researcher at CERN, working on the Large Hadron Collider here in Geneva, Switzerland. I'm sad that WOMAD is not happening in person this year, but like many of the other events I was planning on attending, this one was also canceled. But I did want to take this opportunity to talk with you about some of the things that we as the global particle physics community have done to respond to this global challenge that we're all currently facing. So now, at first, particle physics may seem pretty far removed from public health. Normally, the things that we study as particle physics researchers is, what the basic building blocks of matter are, how the world came to be as it is right now, and what kind of physics laws govern the universe at the earliest moments of its existence. So what you see here is CERN. It's the European Lab for Particle Physics Research, and normally it looks like this. It's a pretty busy hub for researchers from all over the world, including many from the UK, to come here and exchange ideas about particle physics and carry out their research. And the main experiment that is currently underway here at CERN is the Large Hadron Collider. So you might have heard about this in the news. This is an underground particle accelerator that is housed in a circular 27-kilometer long tunnel that goes through both Switzerland and France. And powerful magnets inside of this tunnel accelerate particles called protons to almost the speed of light and brings them to collision at 4 so-called interaction points. We then hope to learn more about nature by closely analyzing the debris of these collisions. So what we have done at these interaction points is that we've constructed giant detectors that basically act as three-dimensional cameras and analyze a stream of 40 million collisions per second. These quote-unquote cameras are some of the biggest experiments scientists have ever built. They're the size of a 5-story building, just 100 meters underground. And you actually need thousands of researchers to operate these types of detectors. So I myself am one of roughly 3,000 researchers that work on the Atlas detector. And the Atlas detector has been one of the detectors that has been used to discover the Higgs boson in July 2012. So almost exactly 8 years ago. So these millions of collisions generate an enormous amount of data, so many petabytes, that means millions of gigabytes per year are being recorded, and we can then use and analyze this data to better understand the universe around us. So when the pandemic started out in earnest earlier this year, CERN started to look pretty different. So instead of being this bustling hub of international collaboration, it became almost deserted. And as everybody else around the world, we also self-isolated at home in order to help stop the spread of the virus. And besides trying our best to work or continue to work on our usual tasks, like analyzing the data of the Large Hadron Collider, we also wanted to see how we as a particle physics community could help respond to this global pandemic. And in a crisis like this one, the one thing that we've learned very early on is that it's very important to listen to the experts. So we wanted to really make sure that whatever we would do would not add to the overall noise and end up being a distraction, but rather we wanted to see if we can find ways in which we could use some of the things that we know we are good at to help actual virus researchers carry out their work. And so in short, we did not want to embody this obnoxious stereotype of a physicist that is shown in this XKCD comic, which for the record I'll say is not true at all, at least not always. So one of the projects that we felt we could contribute to meaningfully is a project that is called Folding at Home. And so that's a project that helps scientists understand proteins better. Proteins are large molecules that are made up of many smaller atoms that then govern a lot of what's going on in our cells. And viruses are also made up of these proteins. And so one part of the project that is Folding at Home is what we call a citizen science project. And that means that non-experts like you and me can contribute to the science in an easy but also meaningful way without having to understand the details of the science. So in this case, the functionality of these proteins is governed by how they move in space. And even if the structure of the protein is known, the movements of the protein cannot really be easily predicted. So proteins are pretty big molecules, and they tend to fold onto themselves, and exactly how this folding happens and how they end up in space, that controls the behavior of such a protein and ultimately the functionality of, for example, a virus. And so, but as complicated as these proteins are, we know that all the atoms that make up the protein still have to obey the laws of physics. And so biochemists were able to write computer programs that simulate step by step, atom by atom, exactly how the atoms in the protein respond to the forces around them using, for example, the laws of physics. And if you do this carefully for each of the atoms that make up the protein, for example, by taking into account electrical attraction or repulsion, you can learn how the protein as a whole moves and folds, and then ultimately how it behaves. And so the only catch is that simulating such molecules requires a huge amount of computing power. Even the power needed to simulate only a few thousandths of a second of protein movement far exceeds what's possible even on the fastest computers that you can buy today. Even for the simplest problems, it would take over 100 years to finish the computation on your home computer. And so this is exactly the point where a project like folding at home comes into the picture. Once the computer program for simulating the movement of the molecules has been written by the experts, the only thing that is really required is raw computing power. And so folding at home is software that allows laypersons like you and me to donate our computer's processing power to study the folding process of proteins whenever you're not using or we're not using our computers. And so that means instead of sitting idle and doing nothing when we're not using them, the computers request a small chunk of the computation over the internet and compute a sub-result, and then sends the sub-result back to the researchers, and they can then aggregate all of these different pieces and assemble them into a larger picture that helps them understand the virus better. And so you might wonder how this helps with this coronavirus specifically, and I'm sure you've all seen this famous illustration of this virus. This is the small ball with the many little red blobs scattered around its surface. And so these red blobs are what's called spike proteins. And so these spike proteins are the way through which the virus docks onto and ultimately enters the human cell. And so understanding these spike proteins is an important piece of the puzzle to understand the virus as a whole. And so in particular, these spike proteins can have what researchers call pockets. And so these pockets can open and close. And such pockets can be are used to attach to the human cell, but they are also useful sites for drugs to attach to the virus. But they're not easily visible by just looking at the protein, and they only really reveal themselves by looking at the motion of the protein through time. And so the types of simulations that the folding at home research perform are very, very useful to understand these pockets and how they appear, and possibly those can reveal new attack vectors to combat the virus. This method of large-scale distributed computation that folding at home uses is actually very familiar to us as high-energy physicists. In fact, the World Wide Web was invented at CERN approximately 30 years ago to help scientists share data, research, and computational results easily across the globe. And so when the Large Hadron Collider got started in the early 1990s, all the universities and labs around the world that were participating in the project got together to construct a pretty dense but also worldwide web of data and computing centers, what you might maybe now call the cloud, and we call it the Worldwide LHC Computing Grid, or WLCG. And so this was built in anticipation of all the data that we knew was going to come from the LHC. And so overall, as a community, we combined something like 1 million processes across all the continents. And in the UK, the Grid PP project has been coordinating the contributions from labs such as Rutherford Appleton Laboratory, or universities across the country like Lancaster, Manchester, Edinburgh, Glasgow, Sheffield, and many, many more. So it turns out that when we use this computing grid for our research, we use it in a very similar way as folding at home. When we want to analyze the data that we record with our detectors, we also split it up into smaller chunks and then distribute the pieces around this worldwide computing grid, and then aggregate these sub-results to get a coherent picture of what's happening in these particle collisions. And so in fact, on top of our own resources, we also run a similar volunteer computing project, which is called LHC at Home, that allows the public to donate their computing resources, this time for particle physics research. And I encourage you to check this out as well. So in the end, when we learned about folding at home, this really sounded like the perfect way for us to get involved and make ourselves useful for virus researchers using the tools that we already had. And before the pandemic, we already put in quite some work to be able to quickly switch out the software that we use on the grid. And so this enabled us to drop the particle physics software and load on to the grid the folding at home software and start contributing the computing resources to this new cause. And we started out pretty small, but then many computing centers from the WLCG joined over time, and now the LHC computing community is one of the biggest individual resource donors for the folding at home project at large. But we also weren't alone. In fact, we were part of a pretty large wave of new donors when the pandemic started. And now the number of resources available for folding at home has skyrocketed. Has increased 100-fold, and by now over 3 million computers are part of this new network, generating very valuable data on this coronavirus. And so, but not only on the coronavirus, but also other diseases like cancer or Alzheimer's. But understandably, most of the priority is currently on COVID-related computation. So that means that by harnessing all of this computing power, folding at home as a project actually has more computing power available than even the biggest supercomputers in the world. And I think it's really a nice testament to what we can achieve if we pool our resources towards a common goal. And I do encourage you to join in as well if you haven't yet, using your own home computer. So let's look at one of the results of this computation. So here's a short animation that shows the movement of the spike protein of the coronavirus over time. And as you can see, it starts out pretty close, but then over time, through the complex interplay of forces, the molecule opens up and reveals this binding site within the protein. And that means through all of these volunteer resources, researchers could unravel a new structure inside of this protein that might be helpful in developing new drugs against the virus. In particle physics, we're not only specialists for worldwide computation, but also worldwide data management. And so all these little data pieces that were computed by computers around the world, they actually need to be pretty carefully tracked and moved from hard drive to hard drive. And given the petabytes of data that we regularly produce at the LHC, we've gained quite a bit of experience in how to do this over the last decade or so. And this is why, besides just contributing to the computation itself, we are also working with the folding at home researchers to see whether we can adapt some of these systems that we've developed internally for particle physics to help them tame this incredible amount of data that is now being generated by this 100-fold increase of volunteers that all generate data. And so they're also approaching this petabyte scale, which again is millions of gigabytes. So finally, I also wanted to talk about open science. So for a public health crisis like this, the open sharing of the data and the scientific results is actually very important for quickly making progress in the research. And open science has been important for high energy physics for a long time, and CERN actually has been offering a free platform called Zenodo, not only for high energy physics researchers, but for researchers from all sciences to openly share their data and make their science reproducible. And ever since the coronavirus hit, the platform has been pretty heavily used by researchers from around the world to share their data sets. And by now we have almost 700 individual data sets that are related to the coronavirus that have been uploaded to the platform. And so this is great to see, but this unfortunately already brings me to the end of my talk. CERN and the wider high energy physics community have been pretty engaged in many other activities that I didn't have time to go into, like phase mass production, ventilator design, and you can learn more about them using some of the links that I'm going to put into the description. But I hope I was able to share with you some of the ways that we and you can help researchers in the fight against the coronavirus. So I hope you're keeping safe at home, and I hope to see you at the next year's WOMAD World of Physics in person in 2021. Thank you very much.